Okay, now in this lesson, we are going to focus our attention on two forces producing simple harmonic motion. To show that a given set of forces acting on a body produce simple harmonic motion, then we should show that the equation of motion of that particle can be expressed in a form of the acceleration equaling to negative omega squared then times the displacement. When you do that, the rest are going to be very okay. I think we saw that in elasticity and Hooke's law. I also covered those lessons. You can go in the playlist and you check out for those lessons. So we have seen that also this is our equation which relates acceleration and displacement from what we've been doing. Now let us consider the first case. So, or if they ask you to show that the part describes a simple harmonic motion with its forces acting on it, or you show that those forces, you should express it in this form, as simple as that. Let us case one, we consider vertical string. So this is our string. Of course, L is our natural length. Then D is the extension we have made there. So this is the particle of m kilograms. Of course, it's going to be having a weight of md. So from A, if you consider this at F being equilibrium, it means that the vertical forces upwards are equal to vertical forces downwards. It means that now this is equal to that since there is no acceleration. And then we know that from Hooke's law, tension in the string is given like by that. We get the modulus of elasticity times the extension made over the natural length. Now, if you have an elastic string, it means that when you stretch it, if this, let me show you this. If we have this as the string, this is its now natural length. But when I stretch it, you see, I'm making it to extend, so I'm getting a certain extension. So this is the extension we are talking about. So L is this. Before I stretch it, when I stretch it, it makes a given extension which we have as E. So Hooke's law says the force is proportional to the extension in the string over the natural length, then times the modulus of elasticity. So this works if the strings are elastic. Inelastic doesn't work because we can never extend them. So if the body is given a displacement x from A, and then there is now, if at this point we give it another displacement, if assuming this is our natural length, I give it an extension like that. Then again, I give it another displacement x. It means that now the new extension we are having, we are going to add this x plus the new displacement we made, which is x. So now this is the extension. Now, it means that after stretching it further, even the tension in the string is going to change. That's why when it's just here, the tension is given by that. But when I stretch it further, the tension is going to also increase. That's why I have T1 now. Now this is my extension. So I have x plus A over L. Now we're using Newton's second law. It means that now the resultant force is equal to the mass times acceleration. Now, this one now I'm considering in this part when I'm giving it another extension. So now, when I get md, when I solve vertical downwards, means that this is going to be equal to the line, tip line with a new extension which will be giving it, which is x. So md then it will be opposite minus tip line is equal to mx double prime, where a is now our acceleration, because we say this acceleration is proportional to the displacement of the particle. So now our new extension we get is this. Then we have it there when we open it. But remember that this one from 1, you see that this is equal to that. When we put it there and we expand this, when we expand this and this, we get Lx negative. Then this lambda negative E over L. So this and this they cancel, and we have that remaining. So this is equal to this, and if you divide this n this side, you get this. And so this one is in the form of this x as this. So implying that the whole of this is omega squared. So as you can see, if we compare, the whole of this is omega squared. you want to get omega, you get a square root. But I know that period is given by 2 pi over omega, or the angular velocity. If you do that and you get the reciprocal, that's what we shall be having. This case also applies for the vertical springs. So that's why I'm not having the case for vertical springs. Let me handle now horizontal springs or springs the same. What's the spring of natural length L and modulus of elasticity lambda? Now the same, if I give it, now this is the idea we have. Then this is the natural length we have before. If I give it now as a displacement, this is the displacement we are giving it from home up that point there. The surface is smooth, meaning the only force acting is going to be this. If it, when a particle is given displacement x from O and then the density, means that now if I resolve horizontally, resultant force is equal to mass times acceleration. The force here is that we don't have any force. This is our displacement we are considering there, and particles causing. Then we shall be adding now, not that from hook slope, the all of this is gravitation. This is the force now acting on the string. Putting it there, you see that we have a case there, and you see it's in the form of x prime, x double prime, the acceleration equaling to omega squared negative times the displacement there, as you can see. And so we can also get the same when we draw them, and also all that. So this is the case. Now we are going to see what happens if we have a particle held by two strings. The next lesson, see you there.